Hello everyone, and in this video we are going to be talking about osmotic pressure. And so what I have to the left here is an empty manometer. It's basically a fancy tube that we put a U into, and so if we were to take this manometer right now and fill it up with water, what we expect to see happen is that after some time the water is going to be at the same height on both sides of this manometer. And so right now water, that fluid, is perfectly equilibrated with this environment. The atmospheric pressure pushing down on both sides of our manometer is equivalent. And so there's no reason for water to want to go anywhere, and that's what we have. Now, what I'm going to do is introduce this thing to my manometer inside that tubing called a selectively permeable or semi-permeable membrane. And so this is a very important topic to note before you jump into this stuff. So a semi-permeable membrane, or selectively permeable, is something that allows only specific things to move through it. So in our case, when we're thinking about osmotic pressure, we're going to make an assumption that only water can cross our membrane. And the reason that this is a very important assumption to make and to really think about it is because if things other than water can cross our semi-permeable membrane, then the concentration gradient will change inside of this manometer that we have. And if there's a different concentration gradient, there's going to be a different driving force for mass transfer and consequently a different osmotic pressure in our system. So when you're talking about these problems, just remember that semi-permeable membrane means that this thing only lets water through. No salt, no any other solute can move through except water, your solvent. And so in this manometer, I'm going to put my semi-permeable membrane right there. That'll be our little star. And so what is going to happen here is I put my semi-permeable membrane here, nothing's going to happen. The reason for that is because we haven't added any solutes. So right now the water is pure, we'll assume, and so there's no solutes and there's no concentration gradient here. So right now the water is perfectly okay being where it is, and we've got an equal pressure on both sides of this manometer. And I will call this side A and I'll call this side B. So what happens next if I wanted to create some osmotic pressure in my system is if I were to take some salt, for instance, and put this salt into my differential, or my manometer, is we're going to have NaCl, and it's going to dissolve into Na plus Cl minus. So these cations and anions are going to now exist in our manometer, specifically and only on side B. Why? Because they can't go through our semi-permeable membrane. And so what happens to water is that water wants to solvate stuff, and water doesn't like it when there's a concentration gradient. So if I just started a party on side B and the water molecules on side B are really happy because they're getting to form all these hydration spheres around those sodium and chloride ions, the water on side A isn't going to be too happy. And so what the water on side A is going to want to do is it's going to want to also join that party. It's going to want to solvate stuff. It likes that charge that the sodium and the chloride bring to that party. And so the water on side A is going to move through your manometer, through that semi-permeable membrane that only water can cross, and it's also going to help solvate this sodium and chloride ions. And so as it does this, there's a movement of volume of water. There's a transfer of mass of water occurring, and consequently we're going to see the volumes change. So on side A, if water is leaving, then the volume is going to decrease, and then by conservation of mass we're going to expect to see an increase in the volume on side B. And so the key thing to note here is that as this water moves over and eventually it gets to a point at which it's happy and it stops moving, that difference in the height between these two levels on our manometer, sorry, this difference in height here is going to be what we use to calculate our osmotic pressure. So this height difference, I'll call it H, is something that we'll use in the equation pi equals rho g h to determine what is our osmotic pressure in this environment. And so this is the key thing to get started with. And now what I'm going to do is talk about an equation that we'll use for actually defining what is osmotic pressure. So the key equation to look at here is the following. So pi, which is the way or the character we use to define osmotic pressure, is going to be equal to I, which is the Van 't Hoff factor that we'll talk about in a second, times M, the concentration, times R, the ideal gas constant, times temperature. And these units can vary based on what ideal gas constant units you are going with. So let's just spell these things out. So we've got pi, osmotic pressure, and then you've got your Van 't Hoff factor as I, and right now, why do you need to have this I in your osmotic pressure equation? So the first thing to note here is that when you are dealing with something like NaCl, sodium chloride, you can have this thing decide to form multiple parts of itself when it dissolves. So I accounts for number of molecules made from solvation. And so what do I mean by that? So if I were to take one NaCl and solvate it, like what we just saw, we know that one NaCl will become one Na plus one Cl minus ion. And so what this means is that me giving one molecule of NaCl yielded two ions, specifically solutes. So water is going to have two things, not just one thing, but two things that it's really interested in solvating. And so this Van 't Hoff factor is what lets us account for this. So it depends on your solute. So you need to know your solute really well. You need to know that chemical formula and know what kind of ions are going to exist once you solvate this thing. Something I want to make note of with the Van 't Hoff factor is that if you're dealing with something that isn't something that dissolves into multiple species, like how we're seeing salt go into sodium and chloride, which is two species, but if we're looking at something like glucose, which doesn't turn into two species, it just stays as glucose, like when you dissolve sugar in your coffee, you're not really changing, you're not breaking down that glucose. So I, in that case, would be one, and it's almost like it doesn't exist in that case. But just know that it does exist for solutes that do create multiple species when they are solvated. So that's what I is. Now, when we look at what is M here, so M is your concentration. So this guy is the concentration. Specifically, it is the moles of your solute divided by the liters of your solution, which in our case, it's how many liters of water do we have? And in our case, it's how many moles of NaCl we're adding. And then R is our ideal gas constant. And then finally, temperature, or T, is just temperature. And so this equation right here is the thing to remember on exams. And if you wanted to spell something out, you could spell pi equals M, or MERT, M-I-R-T. But yeah, so that is the key thing to make note of for what is osmotic pressure and how do we calculate it. And now we're going to walk through an example problem, and the goal of our problem, our solution, will be to tell us what is going to be this height difference that is created once I add some salt into side B. So this is our question. We'll do this as a little aside. Question is, if I add 0.1 mole per liter of NaCl to side B, what is the height difference? And so this thing you need to specify a little bit more. So in my case, I'll say T is equal to 298 Kelvin. And besides temperature, so you've got T, you've got concentration. That is all you're going to need to solve this problem. So I'm going to pause here, and if you think you can solve this, go for it. And now we will walk through our actual solution. So dissecting our problem statement, we've got 0.1 moles per liter, which is equal to the molarity of NaCl. We've also got temperature, which was 298 Kelvin. And so the very first thing to ask here is the following. So pi equals IMRT, and we've defined I, we've defined T. Now the question here is, what is I? So I is going to be 2 in this case because, as we just talked about, 1 mole of sodium chloride is going to dissolve into 2 ions, or specifically 2 solutes, 2 things that water will want to solvate. And so this key thing here means that I is going to be 2, and I'm sorry the screen goes crazy, but basically we've got I now, so I is equal to 2, and R is going to be the ideal gas constant, which is something else that is typically tabulated that you just look up. So we've got a fully specified problem that will help us define what is pi. We also want to know, though, what is our height difference? So we'll get to that in just a second. So first, let's calculate what is osmotic pressure. So osmotic pressure, plugging and chugging, we're going to have 2, that's the number of ions that came from each mole of NaCl, and then we're going to multiply this by our concentration, which was 0.1 moles per liter of NaCl, and then we've got our R term, which is going to be 8.314 times, and then the units on this guy are cubic meters per Pascal, or times Pascal, sorry, divided by moles times Kelvin. And then the last term in this is T, and this guy was 298 Kelvin. And so when you do the math here, what you come up with is approximately 495 pascals. So this is equal to pi, which equals your osmotic pressure. And so now that you know what your osmotic pressure is, the next thing to ask here is, what is our height difference going to be? And so with these manometers, one of the cool things about them is that you can make use of the fact that the height difference can be a function of the pressure. And when we look at this thing, we're going to recall this equation right there where we said that pi, or P, our pressure, is equal to rho GH. What this thing means, so I'll just write this out, pi is equal to rho GH. Rho is going to be the density of your fluid, so I'll just write rho sub F. We know the density of water is 1,000 kilograms per cubic meter of water, and then we know G to be 9.8 meters per second squared. And now we need height, but we've got our pi. So if we rearrange this equation, we get height is equal to our osmotic pressure divided by rho of your fluid times gravity. And this guy, if you do the math, is going to be equal to 0.05 meters, which is equal to 5 centimeters. Sorry. And so what does this mean if you think about the intuition? So what it means is if I just put 0.1 moles of sodium chloride into side B, and I got that concentration of 0.1 molarity, and I left it there, and it was at 298 Kelvin, which is 25 degrees Celsius, which is about room temperature. What this means is that after a certain amount of time, the water is going to flow from side A into side B, and we're going to see a height difference between side B and side A of 5 centimeters. And so that height difference is caused by the osmotic pressure of water wanting to solvate those sodium and chloride ions that I've just put on side B. So that is how we think about osmotic pressure. And then food for thought as you progress through all this stuff is to think about what happens in cases where if your semipermeable membrane or your selectively permeable membrane isn't perfect, because if we know anything about reality, it's that it's not perfect. So what happens in these cases, and what happens to your osmotic pressure as a result? And so just to kind of briefly talk about that, if you looked at your semipermeable membrane and you found that salt was able to get through it, what that would do is it would decrease your osmotic pressure. It would decrease the gradient or the driving force for water to want to go from side A to side B. Why? Because as those salt molecules and the anions and cations make their way over to side A, water on side A is going to be able to solvate those, so it's not going to really care about wanting to go all the way over to side B and make a faff about getting through that semipermeable membrane of ours. So that's a key thing to note, is that ideally in practice you've got that perfect semipermeable membrane that only lets water through, but in reality, and especially depending on the solute you have and the degradation of your membrane, you can have a bunch of other things that would contribute to actually affecting your osmotic pressure and the movement of water through these things. Another thing you see as a final note I'll make on this is how can we use this stuff to do something like create potable water for society? So with this stuff, we've seen now how water with a bunch of solutes is going to want to be on side B, but what happens if I created a huge pressure on side B and I just start pushing this stuff down really hard with a lot of pressure and a lot of energy? What's going to happen here is that I'm going to overcome the osmotic pressure of this water, and after I overcome it, I'm actually going to start forcing water through the other side of my semipermeable membrane, and I'm going to be increasing the volume of water that has no solutes in it. And so this is what happens at desalination plants. This is one of the things that the desalination plants are doing, is that they're basically taking that salt water and they are converting it into water that doesn't have salt in it by basically doing what is called reverse osmosis. And these processes require enormous amounts of energy to do this stuff because water really wants to solvate stuff. And that's what we burn so many calories trying to make water not do what it wants to do, which is be on the side of our semi-permeable membrane that is pure and not have any solutes to have fun with. So that is going to wrap things up for this topic of osmotic pressure. I hope this is helpful. Let me know if you have any questions, and thank you all for watching.